In this video, I will talk about projection of vectors, and in the end, I will also show you how to solve a very interesting problem on projection of vectors. So, I will be talking about the 3D space in which you have three perpendicular coordinate axes, and I will represent a vector by a ray, you can call it, not an infinite ray, but a ray with a particular length and a particular direction. One very important thing about vectors is that you can translate them. You can translate them, which means you can move them in a way like you're not rotating it. The translation is different from rotation in a way. You can see like this motion is translation, this motion is translation, because I'm not rotating the vector, right? I can translate it anywhere, but I cannot rotate a vector like this. Rotation is not allowed, because when you rotate a vector, the direction towards which it points, that direction changes. And by definition, a vector is magnitude. A vector is a quantity which has magnitude and direction. If you change the direction, or if you change the magnitude, the vector would change. So when you rotate, the direction changes. But when you translate a vector like this, neither the magnitude nor the direction of the vector is changing. Somebody can argue like this, like before the vector was pointing in this direction, and after translation the vector is pointing in this direction, and this direction goes towards, let's say, point A, and this direction goes towards point B. And somebody can say that this direction 1, let's call it direction 1, is different than direction 2, just because they point on a two different points in the space. But this is not how we use the word direction, um, in mathematics and also in real life. For example, suppose there is a big um, train station, a railway station. It's a big building, and there is a person standing in front of one of the entrance door of that railway station, and then there is a tree on this side of the railway station, and a person is standing right in front of the tree. And suppose this direction from this person A to the store D happens to be the north direction, and for this person B and this tree, this direction, this also happens to be parallel, and you, in that case, you will say that the direction this to this direction is north, B to the tree is north, and A to the door is also north, right? So these the direction is the same, but they are pointing towards different objects. So we don't have to think of direction absolutely. We can think of direction in a relative sense, and then you can understand why it's allowed to translate the vector but not rotate the vector. Once that is clear, there's another concept which is very important, is like two vectors are always coplanar. Suppose these two vectors, they don't look coplanar, because this point is its starting point is here, and the starting point, the end point, you can call it tail. The tail of the vector red vector is here, the head of the red vector is here, and the tail of the yellow vector is here, and the head of the yellow vector is here. And if you connect these 4 points, you don't get a plane. You get, when you connect 4 points in a 3D space, you won't always get a planar quadrilateral. But since you can translate the vectors, then you can consider this line which connects the tail of both the vectors, and then you move one of the vector on that line, translate the vector, and you match the tails of the two vectors. And now you can see you don't have 4 points in this space which you have to connect, you have only 3 points. The tail is matching, both the tails are here, and head 1, let's say this is head 1, and this head 2 is here, and you have to join these 3 points. And when you join 3 points in 3D space, you will always get a triangle, and that triangle would be planar. So these two vectors are planar. So they might not look planar in the uh, first view, but then you can move them in such a way that you can make them planar. So two vectors are always coplanar. Now let's think about what is the meaning of projection of two vectors. So suppose you have a green vector and you have a red vector. Okay, I would also like to make it clear that the yellow, this yellow face is the front face of the cube, because some people can see a cube in different way, and some people see a projection of a cube in a different way. What do I mean by that? So this yellow face is the front face, then back face is this one, and this is also solid yellow line which I am right now making, but this is the back face. But some people can say that the back face is front, and you can also do that. You can see the cube in such a way that the back face, which I am this back face which I write here, you can see it as the front face. But to avoid confusion, I would say like the yellow dotted face, this face is the front face. Anyways, so now it's easier to talk what I am saying. So now the two vectors, you see the first vector, the green vector, is on the front face. It's on the upper edge of the front face, and it goes from halfway of that edge to the end of the edge. And the red vector is the face diagonal of the back face. And we have to figure out the projection of red vector on green vector. Notice that the projection of red vector on the green vector. So you in projection two vectors are involved, and which of the projection of what on what, it matters. You can't there's no commutativity in this kind of relation, because if you think of projection of green vector on the red vector, that would be different. Perhaps, we don't know, but let's explore it. I think that would be different. Why do I say that? Because first of all, what is the meaning of projection? So you have to project the red vector on the green vector. How do you do that? One easy way is like you can match the tails of the two vectors. You can bring the tails together. What happens now that when you bring the tails together, you don't have to project the tail. You only have to project the head. And the green vector, where the projection is to be taken, you can turn it into a big screen, a big line, and you just only have to project the head of this red vector on the screen, on the green vector. So you can extend the green vector. It doesn't matter, because sometimes your vector will be small, sometimes it would be large enough to get the projection on, but the length of the vector on which the projection is to be taken doesn't matter. So you just have to project the head now, and that you do by using perpendicular line, and then you see that this yellow line from here to here is the projection of the red vector on the green vector. So if the edge length of the cube was a, you see that we have this length was also a, right? So the projection of the red vector on the green vector is a. Let's see another very interesting way. If you don't want to move vectors, you would have to project the tail and the head both. So now this is the green vector, this is the red vector, and you can turn the green vector into a big screen, a big line, and then you have to project both the head and the tail. And you can see this is the head here, and if you want to project the head on this screen, on this line, then you will have to think of a line which is perpendicular from this point on the line. So you can't go like this, because this is not perpendicular. You can't go like this. You can feel that this is the perpendicular line. The edge of the cube here is the perpendicular line, and then you have got the first you have got the head, which the projection of the head, which is here. And now you have to think about the tail, and you can take a minute, you can pause the video and think for yourself, how would you project the tail? So the answer is very simple. If you draw this line, this will be perpendicular to the green screen, this white line here. So now you see, if we have got the projection, the tail is projected here, so let me write a TP, and the head is projected here, so this is head projected, this is tail projected, and then you join this, and then you get the projection. You can also make a projection vector, and you can define its direction, but I will not be dealing with the vector. I will just talk about the length. So this is the projection of green vector on the red vector on the green vector, and done in this way without matching the tails. If that distance is a, this distance is also a. Okay, now let's derive a formula for projection of vectors? For that, it's very simple. We will use the first approach, in which the tails of the vectors are matching, so you don't have to draw two perpendicular lines. So you turn the green vector into the screen and you take the projection, and that is your projection. So notice that if this distance was a, we can very simply see that this distance is also a, but let me show you the obvious facts involved here, that the length of the red line was root 2a, because it's the face diagonal of the cube, and then that angle theta is 45 degree, so that length is root 2a times cos theta, and this is the formula for projection which we can use. So what you can do, you can think in a general sense, like the red vector, let's call it P, and the green vector, let's call it Q, and the angle between them is theta. The angle between two vectors is defined by matching their tails. This is very interesting, because if you move the green vector here, okay, so let me use green color for that. If you yeah, so if you move the green vector there, and this is theta, then you can say that this angle is 180 degree minus theta, and maybe this is the angle between the vectors. But when you have to find the angle between the vectors, there could be two angles. So that angle, which when you are matching the tails of the vector, or you can also match the head of the vectors, if you take the green vector here and then the heads are matching, and then this angle is theta. So when you are taking the angle between the vectors, their head should be matching or their tails should be matching. That's how you define the angle between two vectors, because there are two angles between them. So this theta is the angle between these two vectors, and then you turn the Q into a screen, and then you draw the perpendicular, and then you take this projection that happens to be, this length is mod of vector P, and this length therefore would be using the cosine definition of cosine, that will be mod P cos theta. And then if you multiply mod Q above and below, then you get, this term becomes P dot Q, the dot product of these two vectors divided by Q. Notice I have been careful, and I have used a modulus here, because the cos theta could be positive or negative depending upon the angle between two vectors, but I don't want to go into positive and negative. I am not defining the projection vectors, but which can be defined and be very easily dealt with. I am just thinking about the length of the projection. Okay. So now a very interesting question. So what is the projection of this red vector on the green vector in this diagram? The red vector is now one of the body diagonals of the cube, and the green vector is one of the face diagonals of the cube. There are many body diagonals, 4 by actually, and there are 12 face diagonals, and I don't say that this will be true for all such pairs, but here in this example, what do you think? What is the projection of the red vector on the green vector? Take your time, pause the video and solve and see for the answer, because the answer is very interesting. Okay, so the length of the cube can be taken as A, and now you see one way is like we can use the dot product to solve this question, which is a cheat in a way. It's like cheating, because we are not going into the geometrical interpretation of the idea of projection. We are taking a bypass of the formula which involves dot product. That is also okay, but let's see how to execute that thing. So we have the origin 0 0 0, and let's define these axes x y z, and let's think of this point. This point will be 0 0 a, and this point here, the head of the red vector, that would be a0, right? Okay, so now you can write this red vector. Let's call it, if you call it P, then how would you write this P vector? Okay, so I think first I'm figuring out all these points. Okay, let's figure out all the points, and then this vector is P. And how do you write this P vector and Q vector? The P vector can be written as, you can subtract a minus 0, and you can also subtract a minus 0, and you can do 0 minus a, I cap, j cap, k cap. This way you can write, right? Because if this is your origin and you go from it's not even about origin. If this is a point A and there is a point B and there is a point C, and you have a vector AB and you have a vector AC, then you have to write the vector BC. That BC vector, you can understand, can always be written as AC minus AB. Why so? Because if you see that AC vector, you can apply the triangles law. The AC vector is sum of AB plus BC. So according to triangles law of addition, AC plus BC is AC, and then you can write BC as AC minus AB. So this is what we are doing here when we are writing this red vector. So we see that this vector is of course a k cap, and this vector here is a I cap plus a j cap, and we are subtracting these two vectors. So you can always understand, like you have to subtract. This is the initial and this is the final point on the vector. You have to subtract in a way final minus initial, and then you will get that vector. So you see that when we are doing this, we are using so many things which might sound like if you there is no explanation for that, or the explanation for that is cannot be spoken very simply, right? So there we are going into some kind of vector notations and things. So I would like to solve it more geometrically, but first let's finish this calculation. So you have P here, and then you can also understand in this term, like if you're thinking about this red vector, you can see that you have to go from this direction to this direction to this direction, right? And you can understand, of course, these vectors will be, the first vector is you are going in the x direction, right? And you are going a distance a, and the direction is positive x. So first is a I cap, and then this vector from here to here, this is a j cap, and then you're going down a in the z direction, so that is minus a k cap. This is what we have written here. So you can see it in many ways. And similarly, you can think about the green vector, which will be a I cap plus a k cap. And when you dot product these two vectors, the dot product turns out to be 0, which means that the projection of the green vector, of the red vector on the green vector, should be 0. Interesting. So let's try to see geometrically. Geometrically, if we are taking the projection, we will turn the green vector into a screen, into an infinite line, and then we will think about the lines which are perpendicular from the tail and from the head of the red vector. So let's think about the head first, and then you see this line is not perpendicular, this line is not perpendicular, yeah, but these two lines, these two white lines, they are same. Let's call these points A, B and C. So you see that the A, B and BC have same length A. So in triangle ABC, if you're dealing with triangle ABC, AB is equal to BC, sorry, AB is equal to BC. Yes, this is centered at B. You have B here and you have AB and BC, which are equal. So now in an isosceles triangle, if you draw a line and join the midpoint of AC from B, you will get a perpendicular line, you'll get two congruent triangles, and then you can figure out that the line which will be perpendicular from the head will be this line. So let's mark that point as purple. Now let's think about the other part. Now we are trying to project the tail. So I join this this line. This doesn't seem like perpendicular. This is not perpendicular here, right? So okay, then we draw another line. That line also doesn't look like perpendicular, but both of them, they are the face diagonals of the cube, right? So this distance is root 2a, and this looks longer, but this is the face diagonal of the back face, and this is also root 2a. And we have a similar kind of situation here. You see in the triangle PQR, PQ is root 2a, and also PR is root 2a. So these two lengths are same. Then the perpendicular will be the point, the foot of perpendicular will be the midpoint of QR. which is again the same point. Boy. So now when you take draw these pseudo-perpendiculars, you can see very easily that the projection of the red vector on the green one is 0, right? So if you want to feel it like more geometrically, so then you will have to extend the cube like this, and you can move it the green vector on one corner and the red vector on the other corner. Basically these two vectors should be perpendicular. They don't look like perpendicular, but as we have seen, I can prove you in another way. So now think about this yellow line. This distance is a, this distance is 2a, and the yellow line, so we are doing all the calculation on the front face now. The length of the yellow line should be root under 5a, right? Okay, and then let's think about the length of the red vector was a root 3 because it was a body diagonal. It's still a body diagonal. And the length of the green vector was a root 2. And then you see this triangle, and you can verify the Pythagoras theorem, and it fits here, and it seems like that this angle is 90 degree, which is not so clearly visible in this projection, but sure, it's 90 degrees. You can use this kind of animation geometry GeoGebra to draw these vectors and check. So I used GeoGebra, and from there I can see that this is the body diagonal. No, this is the face diagonal, sorry, and this is the body diagonal, and I have the similar kind of situation, and I see now very clearly that this is 90 degrees. I have generated a plane which is which contains this line, the body diagonal, and the normal I wrote as the face diagonal, and this face diagonal, and I checked it, and we can now you can see a little bit more clearly that they are perpendicular. Anyways, so now we will be dealing with another very interesting thing. Like normally we talk about a projection of a vector on the other vector, but a lot of students I have seen, they don't deal with projection perpendicular to the direction of a given vector. So what do I mean by that? Let's see, like in this diagram, we are taking projection of the red vector on the green vector, and we are turning the green vector into a screen, but we can also think of a screen which is perpendicular to that screen, right? And then we can think of a projection like this one, which we have already seen before. This is projection of P on Q, and that is the modulus of P dot Q divided by the modulus of Q. But we can also think about this projection, and that projection is the projection of P on the direction perpendicular to Q. And that is not so difficult to determine because this is only mod of P sine theta. Because this length is, if this length is mod of P cos theta, this length should be mod of P sine theta. And that can be written in terms of cross product, because you can insert a Q mod Q up and down, and you can figure it out that this can be written as, now you got in the numerator, you've got the expression for cross product, modulus of the cross product, and then you can solve it like this. So this can also be very useful sometimes, the projection of a vector on a direction perpendicular to another vector. Let me show you an example in which is used. So this is the question which was asked to me a few days ago, and then I thought to do it in a proper way. So the question goes like, show that the perpendicular distance of the point C. Now first of all, a vector cannot be a point. So what is missing here? Of course, they are saying, they are talking about the perpendicular distance of a point with position vector. Now it makes sense, from line joining points with position vectors A and B. Okay, so let's try to solve it. It's very simple. So let's try to solve it. Now suppose you have this 3D space, and you have an origin there, and you have a point here with position vector A, and then you have a point here with position vector B, and then you have a line joining these 2 points. Fine. Then you have a point C somewhere else, and I have taken it on the z-axis, let's say, and you have this position vector C here. And what you have to think is, what you have to find is like the perpendicular distance of this point, right? The perpendicular distance of the point from this line. So something like you have to think of a perpendicular line from this point on that line. So let's try to make it simplify this. Let's do some obvious constructions. Let's join these 2 points, and then you can begin to feel that this is a triangle, right? Let's say this point is A, this point is B, and this point is C. So ABC is a triangle, and if you ignore this origin on all these lines, you are just dealing with a triangle A B C, and that looks like an obtuse angle triangle here, but that's a triangle. So let's say this is A, this is C, this is B, and what we have to find out is the perpendicular distance of C from AB, and this kind of a line, this is the line which I have drawn here. So this is a planar situation. If you think about, there are only 3 points A, B, and C, which are definitely planar. So we are working in the plane of the triangle ABC, and then things becomes very simpler. And that is the perpendicular distance. How do we figure that thing out? So let's see this vector from B to A, that can be written as vector A minus B, right? Final minus initial position vectors. So this is A minus B. And let's take this vector, this red vector here is final minus initial position vector, so C minus A. And that yellow line here, which we have to find out, is the projection of C minus A vector. The red vector is the projection of the red vector, not on the green vector, but on a direction perpendicular to the green vector. And that's why we can simply see we have made 2 screens on A minus B vector, one along this vector and the other perpendicular to that vector. And then we see that the yellow line which we have to find is the projection of C minus A in the direction perpendicular to A minus B. And that can be calculated very easily now. So then you can just solve this expression and you can prove that the proposition is correct, and hence you have the solution. So I would like to emphasize, like many times you can use this thing, the projection of a vector on a direction perpendicular to another vector, to simplify your calculations. Thank you for watching.